Today we're going to be doing some more Calculus 2 practice problems, focusing on trigonometric integrals. So this is going to lay the foundation for probably the hardest integration section of Calculus 2, which is trig sub. So we need to have a good foundation of this before we can move on to that. But before we can start trigonometric integrals, we have to know these trig identities, the power reducing formulas for both cosine squared and sine squared, and the Pythagorean theorem, particularly all three. And I left 2 and 3 blank because I wanted to show a trick that my Calculus 2 professor taught me, is that you don't have to memorize all 3 formulas. You just need to know this one, which we should already have memorized, and then just by dividing everything in the equation by sine squared x, you can get 1 plus cotangent squared x equals cosecant squared x. And dividing that top equation by cosine squared x would leave you with tangent squared x plus 1 equals secant squared x. So you really only need to know the top one, and you can find the second and third one by dividing. Okay, so we're going to be using all 5 of these equations. Well, we're really not going to use this one right here. Really, trigonometric integrals are just involved with sine, cosine, tangent, and secant. So we're going to use 4 of these equations throughout all these questions. So first, they're asking us to evaluate these integrals using powers of sine and cosine. So we probably could already do this based on our u substitution skills. We know that if we call u equal to cosine x, then we have the du waiting for us right there. It's actually negative sine x dx. So we need a negative there. We're going to bring a negative out front. Then we have negative integral of u to the 5 du, which is just negative 1/6 u to the 6th plus c. Plug back in our function of u, negative 1/6 cosine x to the 6th power plus c. So easy enough. It'll get a bit harder in something like this when we have to choose what we want to be our u and try and get a du for it. So I'm thinking we're going to use the same strategy of just pulling away one of these signs, right? So I'm going to rewrite it as cosine cubed x, sine squared x, sine x dx. And I want to use this as my du, which means if this is my du, then I want my u to be a function of cosine, right? So I want to get rid of these signs and change them into cosines. Well, thankfully, we have the Pythagorean theorem, which says that sine squared x is equal to 1 minus cosine squared x. And then we still have that sine x dx. So now we have everything in terms of cosine, and we are able to make the substitution out. If we call u equal to cosine x, du is equal to negative sine x dx. So we'll put the negative there, account for it with 1 out front. Now we have negative integral u cubed 1 minus u squared du. Now this is an integral we can solve. We can simply just distribute that u cubed and evaluate the integral. It's going to be negative 1/4 u to the 4 minus 1/6 u to the 6 plus c. And we can distribute the negative and plug back in our function of u. Simple enough. That's pretty much all they'll throw at you with sines and cosines until they get to even powers, which we'll look at the very end with a differential equation. But we can look at tangent and secant. So don't get freaked out when you see a theta, because as long as this is theta, then we're good. Just treat it like x. Right? So we can follow the same strategy. I see a big composite function, And from the first video I made, we know that u is going to be the inside of that composite function in general. And we have the perfect du right there. Secant squared theta d theta. So the secant squared theta and the d theta will make that du. Right, so now we have the integral. We have 27 u's being multiplied, and we have a du. It's a fairly simple integral. Just plug back in the function of u. Tangent 28 of theta plus c. So these ones aren't too bad. But they can get a bit trickier, like in this one. Well, we're not going to call u equal to tangent because we have way too many secants for our du. So how are we going to get it into a form we can use? Well, once you get good at it, you can just recognize the patterns. How about we pull out one of those secants to be with the tangent? Does this look familiar to you? It is the derivative of secant. So that would be a good du. So if u is equal to secant, du is equal to secant tangent. Now we just have u to the 4 du turns into 1/5 u to the 5th plus c. And we'll plug back in that function of u. So once again, nothing too crazy. Now we'll look at a bit of a harder one, a definite integral. So now you see we have no signs to get rid of. We just have an even power of cosine. So what we can do with this is use that power reduction formula, the one that we started with, that cosine squared x is 1/2 plus 1/2 cosine of 2x. That's going to allow us to break this down into something we can integrate. So how about we, let's rewrite this as the integral. I'm going to leave out the bounds for a few rows. Isn't this just the integral of cosine squared x times cosine squared x dx? And isn't cosine squared x just 1/2 plus 1/2 cosine 2x times 1/2 plus 1/2 cosine 2x dx? Now let's FOIL this out. It's going to become 1/4 plus outer is 1/4 cosine 2x. Inner is the same, 1/4 cosine 2x. And last is 1/4 cosine squared of 2x dx. So let's combine our like terms. We have 1/4, we have 2/4 or 1/2 cosine 2x. See, we can integrate both of these. But then this cosine squared 2x, we have a bit of an issue with. We're going to have to do another power reduction on that one as well. So we'll take out the 1/4, and we know that cosine squared of 2x turns into 1/2 plus 1/2 cosine of twice that angle. So twice of 2x. Twice of x is 2x, and twice of 2x is 4x. So now we have broken down that 4th power cosine into the sum of multiple powers of, or single powers of sine, which is something that we can integrate using u substitution. So let's rewrite this as the integral of 1/4 plus 1/2 cosine 2x. We have a plus 1/8 and a 1/8 cosine 4x dx. So finally, this turns into the 1/4. 1/4 is really 2/8. 2/8 and the 1/8 make it 3/8. We have a 1/2 cosine 2x and a 1/8 cosine 4x dx. So let's do the integral. Integral of 3/8 with respect to x is 3/8x. The integral of cosine 2x. I like to write down this s, c, negative s, negative c. When you're deriving, you move down the list. When you're integrating, you move up. From the top, you go to the bottom, and from the bottom, you go, or from the bottom, you go down and up to the top. So this is a little cheat sheet for, sometimes you can lose track of sines and cosines. So for example, the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. And the derivative of negative cosine, we're back at sine. It's the same thing, but vice versa for integrating. So when we're integrating cosine, we're moving up to sine. Well, that's the easiest one because we know the derivative of sine is cosine. So we know we're going to have a sine of 2x. And we also know that when we take the derivative of that, there's going to be an extra 2 out front. So we want to account for that with a 1/2. See, now when that extra 2 comes out, the 2 and the 4 cancel to make the 1/2 that we had in the integrand. Okay, same thing with this one. Cosine of 4x is going to integrate to sine of 4x. And in order to have a 1/8 after the derivative, we want to have a 1/32 before the derivative. Now when we take the derivative, the chain rule causes an extra 4 to come out. The 4 and the 32 cancel to make a 1/8. Finally, we have our plus c. No, we don't, because this is a definite integral, and I should have kept all the bounds, but we're going from 0 to pi over 2, which means we're going to evaluate all of this at pi over 2 and 0. So we have 3 pi over 16, and we have 1/4 sine of pi, and 1/32 sine of 2 pi. And then, yeah, we don't need to do the 0 because when we subtract off 0, all 3 terms go to 0. Lucky for us, sine of pi is 0, sine of 2 pi is 0. So the answer, the final answer, this definite integral is just 3 pi over 16. Right. Finally, that was a pretty tough one. Finally, let's look at the general solution to the differential equation. We're looking for some function y that when we take the derivative with respect to x, right, because that's what y prime is in this case, dy over dx. When we take the derivative of y with respect to x, we're going to get sine squared y, which means y is the integral of sine squared x. Based on the last problem, we should probably guess that we are going to use a power reduction formula since we don't have any cosines. This is just 1/2, now minus 1/2 cosine 2x. I could not explain to you why that works, but it does. So let's integrate 1/2 with respect to x to get 1/2 x, and let's integrate 1/2 cosine of 2x. So when we integrate that cosine x, it's going to be a sine of 2x. And after the derivative, we want a 1/2, which means before the derivative, we want a 1/4. Now when we derive that sine of 2x, an extra 2 comes out. The 2 and the 4 cancel to make that 1/2. So we know we did it correct. This is the final answer. This is the general solution of that differential equation. So that is how you integrate trigonometric integrals.